We now talk about the cross product. Cross product is a supplementary structure that a vector space has, much like the dot product, the scalar product we talked about in the previous lectures. The main difference, well, there are two main differences between cross product and scalar product. The first one is that the cross product is defined just over R3, whereas the scalar product, or more generally inner products, may be defined on a wide class of vector spaces, including the infinitely dimensional ones, like spaces of functions. And the second one is that a cross product gives back as a result not a number, but another vector. Okay, so let's start. In lecture 10.1 and 10.2, we have defined a supplementary structure on a vector space V, called an inner product. As a mathematical object, it is a function that associates to a pair of vectors in a vector space V a number, a scalar in R. We now define a new product structure just over V equal to R3, called the vector product or the cross product. It is a map denoted with this kind of wedge symbol that goes from the Cartesian product of R3 by itself and takes values in R3, which means it takes a pair of vectors in R3 and gives back another vector of R3. Remarks: in the literature, the vector product is denoted in different ways. It can be denoted with this wedge, or also with like a cross, being the most common. But cross is already very much abused in mathematics. For example, it is already used for taking the Cartesian product of sets or vector spaces. Therefore, I will favor the wedge notation as opposed to the cross notation. In this course, we will use wedge, as the cross can be confused with other notation. Notice that the codomain is R3 and not R. Thus, V vector W is a vector. Definition: given V and W in R3, the vector V vector W is the vector in R3 whose components are computed by expanding the determinant of the symbolic matrix. It is a 3 by 3 matrix. The entries of the first row are not scalars. Each of them is a vector of the canonical basis of R3. So E1 is the vector 1, 0, 0, E2 is the vector 0, 1, 0, and E3 is 0, 0, 1. This is why we call this matrix symbolic, because the entries are not scalars as we used for defining a classical matrix, but they are just symbols. And these symbols can actually be multiplied together and summed together accordingly to the rules of the determinant. So not all of them can be summed. For example, I cannot sum E1 with V2. Now I will explain what the second row and the third row is. But the operations involved in taking the determinant of this matrix are well defined. The entry of the second row are the components of the vector V. So V1 is a number, V2 is a number, V3 is a number. So they're all scalars. And the same for the third row are the entries of the W, are the coefficients of W. Here is a list of some of the main properties of the vector product. Let's assume that V, W, and U are vectors of R3, and alpha is a scalar. Then the first property is that the vector product is anti-commutative. So there is a relation between v vector w and w vector v, but it's not an equality. It is an equality up to taking a minus sign in front. So it is the opposite. And this is called anti-commutativity. And then the other properties are the distributive property of this vector product with respect of the vector sum, the sum of vectors. Of course, we state this for the second factor of the product, but since there is a commuting law by the property 1, this implies the same property also for the first factor. And this reads explicitly as follows: v vector the sum of w plus u equals the sum of two vectors. The first summand is v vector w, so v vector w, and the second one is v vector u. Third property is some sort of commutativity with respect of multiplication by scalars. We have the first factor is alpha times v and vector w. This equals to the same vector product where alpha multiplies w instead of v, and also both of them are equal to alpha that multiplies the result of v vector w. The fourth property relates the Euclidean scalar product of two vectors with the vector product. Let's read this equality. So the scalar product of v times the vector product of v vector w is always 0. As it is 0, the scalar product of the same vector, v vector w, multiplied by w instead of v. What does this mean? Okay, this is a very important property, and since we know the geometrical interpretation of the scalar product in Rn, in particular in R3, we can give a geometrical interpretation of the vector product, a first geometrical interpretation of the vector product. In particular, we see that when we multiply by the vector product two vectors, the result, so v vector w, will be perpendicular both to v and to w. We know that the scalar product of two vectors is equivalent for these two vectors to be orthogonal. If we take as a scalar product the Euclidean one, we can prove that these relations are 0, these scalar products are 0. Therefore, v vector w is orthogonal both to v and to w. Therefore, that means that assuming that v and w are linearly independent, these geometrically we know that the vector product of them will be perpendicular to the plane generated by v and w. This is a crucial property of vector products that we will investigate further in future lectures. Now, fifth property, v vector w is 0 if and only if v and w are linearly dependent. Therefore, there exists alpha such that alpha v equals to w. All these properties follow from the properties of the determinant. I could have given the definition of vector product just giving the explicit formula instead of passing through the expression of the formula as the determinant of a matrix. But then it would have been kind of tedious and kind of complicated to prove all these properties. But if we know that that explicit formula that we will see comes from the determinant of a symbolic matrix, then all these properties follow from the properties of the determinant that we studied in previous lectures. One last remark before finishing the lecture is that the vector product is not associative, i.e., in general, if we take the vector product of v with w and the result we multiply by u, this is not going to be equal to v multiplied by the product of w vector u. For example, let's take the vectors of the canonical basis. If we multiply e1 times e1 vector e1 vector e2, we will be getting negative e2. On the other hand, if you multiply e1 vector e1 and the result vector e2, then already in the first factor we will be getting 0 because of property 5. So e1 is of course linearly dependent with e1, so we will be getting 0. And 0 vector, any vector, is going to be 0 vector because in the determinant one of the two, the second row or the third row, is going to be 0, so the determinant of a matrix with the 0 row is 0.